Hello, welcome back, everyone. Today we're going to be starting unit number 5. Unit number 5 has to do with special derivatives. So we're going to learn about the derivative of the exponential function. We're going to do some optimization problems regarding that. So similar to unit 3, but with the exponential derivative as opposed to just the other derivative rules such as product, power, quotient, and chain. We're also going to be talking about the trigonometric derivative. So what's the derivative of the sine function, the cosine function, etc. So that's also going to be one of the topics we'll talk about. If you're doing the AP course, then there's also going to be derivative of the natural logarithm, or even if you're not doing the AP course, it says AP3 here, but I also believe there's some regular classes where the natural logarithm is taught as well. As you might be able to guess, it's very similar to exponential since they're just inverses of each other anyway, but that's what's going to be covered in this unit. Okay, so let's go ahead and start here. So for today, we're going to be talking about derivatives of the exponential function y is equal to e to the power of x. Okay, so recall that exponential functions model rapid change like that in population growth, compound interest, earthquake intensity, radioactive decay, to name a few. E is approximately 2.718 blah blah blah, right? It's irrational and named after the mathematician Leonard Euler. Okay. So it's kind of like pi in that sense, right? It's a decimal that is just a never-ending decimal, continues and continues, right? It's not a rational number. Otherwise, we'd be able to put it into a fraction form, but we can't because it's not rational. So that's just a reminder of what E is. So here is a graph of E, and they would like us to sketch the graph of, the derivative here. So, as a reminder, the derivative is just what? Well, the derivative is going to be the slopes of the tangents. So, what's interesting is that the slope of the tangent in this case is going to give us, if we do that, it's going to actually give us the exact same thing when we sketch this graph as the original. So, what's interesting about the exponential function is that the derivative is equal to the original function in this case, and that's why it's special. So if y equals to e to the power x, then y prime is also e to the power of x, right? And hence also y, the second derivative would be e to the power of x, third derivative e to the power of x, and so on and so forth, right? So basically what this means is that the derivative is actually the same as the original function, and that's not very usual. In all our other examples, I always talk about how make sure you keep them separate. They're not the same thing. Don't get confused. In this case, they are the same thing. Now, let's say that we're looking for the derivative of e to the power of something. Well, in that case, we would actually have to use the chain rule. Okay, we would have to also multiply by what the function is. So, for example, if y is equal to e to the power of 3x plus 4, for example, y prime is equal to e 3x plus 4 times the derivative of 3x plus 4, which we know is 3. So this would actually be 3e times 3x plus 4. And then the same thing would happen again if we were to take the second derivative. We would end up with 3 times 3 times, right? Because times e 3x to the power of 4, so it'd be 9. And then the third derivative, we multiply by 3 again, we get 27. And then fourth derivative, we multiply by 3 again, and so on, okay? And so even though the derivatives aren't exactly the same in these situations, they're still very similar, right? We still really only have to just multiply by g prime of x one more time, right? Is all we really have to do in those situations. So I'm going to do example 1 first. Example 1 says, find f prime of x for f of x is equal to 4 e to the x. So in this situation, f prime at x is equal to 4e to the x. Why is that? Well, because we don't have an actual function, we just have e to the x times 4, which is a constant, which does not change when we take the derivative, right? And therefore, it's just the same thing. And I want to be clear too. A lot of people think, oh, the constant disappears because constants, the derivative of a constant is 0. And that is true, but that's only if we added a constant. If we had e to the power of x plus 4 and we were taking derivative, then it's true. The derivative would just be e to the power of x, right? Just be that base exponential function. But no, this is multiplying. We're multiplying here, not adding. So the 4 just stays put, and e to the power of x also stays put. That natural exponential function stays put as well. Now let's try this example. Example 2, it says find the derivative for f of x equals e to the power of 3x. So in this case, I'm going to need that chain rule. I'm just going to first copy down what we already have, and then I'm going to take the derivative of what's in the function, right? When I say what's in the function, the derivative of what's in the exponent. So the exponent is 3x. The derivative of 3x is 3, right? So it's going to be 3e to the 3x. And this is often the mistake that students miss, right? And this was something I certainly did in high school. I would write, oh, it's just the same thing, so it's e to the power of 3x. Well, no, if there is something other than just an x in there, then we have to apply the chain rule. And technically, even when it's e to the power of x, we're still applying the chain rule because we would just be multiplying it by 1, which just gives us the same thing. So we could even apply the chain rule to, to this function, and it wouldn't change our answer, right? Because what's the derivative of x? 1, right? So it's not like the chain rule fails us in that case. It's just that we don't really need it. It's kind of redundant. Good. All right, let's do a few more examples, and I encourage you to pause this video and give these examples a try before I take them up. Okay. All right, so let's do example 3 next. In this case, our derivative would be, well, first of all, I'm just going to copy what we have, and then I'm going to take, our derivative of what's in our exponent, which is 4x plus 1. So derivative of that is 4. So the answer is 4e to the 4x minus 1. Voila. Okay, what about this next one here? In this case, we have e to the power of x squared minus 5x. And what's the derivative of x squared minus 5x? That's going to be, just by the power rule, 2x minus 5. So therefore, the answer is 2x minus 5 times e to the x squared minus 5, like that. And I just switched the order just because it's better formed that way. But if you did stop here, this is still technically the correct answer as well. And then lastly, it says determine the equation of the tangent line to the curve y equals x squared times e to the x at x equals 2. So this one is a little bit harder. There's a few more steps we need to do. So first of all, we need to apply the rule we learned about what the derivative of e to the power of x is, and we also need to apply the product rule. So just a reminder, the product rule is the derivative of the first times the second one plus the first one times the derivative of the second one, right? So if this is f and this is g, y prime would be f prime g plus fg prime, like that. Okay. Now, if you need a reminder, and if that wasn't a good enough explanation for the product rule and how it works, there is a whole video on the product rule, but that is as much detail as I'll go into it with here. All right, so now let's find out what is the derivative. So it's f, the derivative of f, right? So derivative of x squared is 2x times g, which is e to the power x, and then plus f, which is just x squared, times e to the power of xg, or g prime, I should say, right? Because the derivative of g and g itself are actually the same in this case because we have g as just e to the power x, and so it's the same thing. So they would like to know the slope of the tangent at x equals 2. Now, again, the slope of the tangent is the same thing as the derivative. So now what I need to do is I need to find this at x equals to 2. So therefore, we have 2 times e squared plus 2 squared times e to the power 2, which actually, in hindsight, this is just adding up the same thing twice, but that's okay. It won't always be, but it was in this case. So we're going to get 4e squared plus 4e squared, which is 8e squared. So there we go. Now, a lot of people may have stopped here and said, okay, that's the final answer. It's 8e squared. Haha, we got it. And that's fair. And that's fair. And you know what? I applaud you if you got to this point. That is good. Okay. But keep in mind, that is just the slope, right? The slope of the tangent line is 8e squared, right? That is just our slope. However, um, however, we have to keep in mind that they asked for the equation of the tangent line. So we know now that because we have y equals mx plus b for any equation of any line, with m being the slope and b being the y-intercept. So we have y equals 8e squared x plus b. Okay? So that we know. So now we need to find out a point on this line in order to sub that point in order to find b, or the y-intercept here. Okay, so what we're going to do for that is I'm going to say, well, we know that if x equals 2, then y would be equal to x squared, which is 2 squared, plus e squared. So that's going to be 4e squared. So therefore a point is 2 comma 4e squared, right? A point on the original function is that. Now, do we have to use that point? No, we can use any point we want. That's just the point I chose personally, but it does not matter which point you choose. You will get the same answer either way, or at least you should. At least you should get the same answer either way if you're doing it correctly. Okay, so now I'm going to sub in my point. So I'm just going to put sub in point for our next step. So 4e squared equals 8e squared times 2 plus b. So 4e squared equals 16e squared plus b. So therefore b is negative 12e squared. So therefore the equation of the tangent line at x equals 2 is y equals 8e squared x minus 12e squared, right? So make sure you do that last step and put in the full equation, right? It's very important to pay close attention to, is the question just asking for the slope of the tangent line, in which case we could end here and say, that's our final answer, we're done. Or are they asking for the full line? So if they're asking for the full line, we must also do a couple extra steps like finding that point and plugging it in and getting that b value, right? That y-intercept is very key, very important. And that's a common mistake I often find out on tests. So make sure that you don't make it. Okay, well, that is everything for today. Next day, we will be talking about the general exponential function derivative, so the natural ln and log and that sort of thing. So we'll be talking about that in next day. All right, good work today, everyone, and we will see you next day.